As a brief introduction to what we're trying to do in material science interviews, in particular in Oxford, what we're trying to do is to get just a little bit more information about the students. And we're doing that because we're trying to match the students to our selection criteria as best we can. So we have information already ahead of the interviews that we use in making our decisions, like the information on the UCAS form, which includes the personal statement. It includes the GCSE grades or equivalent that the student already has, their qualifications that they've already got. It has what they're predicted to get in the qualifications they haven't yet taken, like the A-levels. And it has a reference from the school, which tells us what they think about the student. But we're also interested in finding out as much information as we can. So we also have the PAT test, which is the physics aptitude test that the students take ahead of the interviews, and it tests their basic maths and physics knowledge and problem solving ability in those two subjects. So again, that gives us a bit of different information compared to the A-level grades and predictions and GCSE results. So the purpose of the interview is to just get as much more information that we don't have from those existing bits of information that we have. So that means that we ask some technical questions to try to see how the student thinks. And in particular, we don't want to be testing necessarily their knowledge so much as what they do with their knowledge. So we give them some unfamiliar problems and ask them to work out some things that they won't have thought about before. We don't expect them to do it without help from us, and so the interview is more like a mini tutorial, like the kind of thing they'll get in the first year when they come to Oxford, and there's a discussion between the tutors and the students. And so that's how the interviews turn out, and we use that to try to find out how the student reacts to that situation and how whether they flourish with that system. So that's the kind of information we can get from these interviews. The students get 2 interviews for material science. Every student gets 2 interviews, completely separate interviews from 2 different colleges. They're each about 35 to 40 minutes long. And in each one of those, you'll probably have 2 interviewers. And those 2 colleges independently make a decision on the grade that they're going to give to that candidate. And then all of the information is collated together, and all of the different tutors from all the different colleges get together, and we try to go through the whole list of everybody we've interviewed, trying to see which students best fit our selection criteria overall, so that we try to make offers to the students that best fit those criteria, based on all of the information that we have available to us at that point. Have you got anything to add, Jonathan?
Yeah, I think it's just worth mentioning that there isn't, so with something like the PAT, there isn't sort of a cut-off mark that we look for. We really see that all the different pieces of information as being trying to build up a sort of whole picture of the candidate, including the interview. So there isn't a set PAT mark we look for. There isn't a set of GCSEs that the grades that we look for. Really, it's about seeing the everything in the all together.
Yeah. So that is a little bit different from how some of the other science subjects may use the PAT score. So we do take it into account both in the shortlisting and in the final grades, but it's only one part, as Jonathan says, of the whole picture, and there is no pass and fail mark with it, which is quite important. I'm Susie Speller, and my colleague here is Jonathan Yates, and we're going to interview today for admissions onto the material science course in Oxford. So to start off with, I'll tell you a bit about what the interview's like, or what we're trying to get from the interview. So the idea here is that we want to find out a little bit about what you know about material science and why you're interested in studying it. But we also want to ask you some technical questions. And the reason for that is that we need to find out some information that isn't on your UCAS form that we already have. So we're going to ask you some questions that we would expect you not necessarily to be able to answer straight away without any help, and that will be a little bit unfamiliar to you. Okay?
Okay.
Have you got a pencil and paper there?
Yep. Sure, I do.
Great. Okay. So I think we're all ready. So to start off with, can you tell us a little bit about why you've chosen to apply for material science as a subject?
When I attend school, I got quite interested in both physics and chemistry. So both subjects are my favorite subjects, and I'm trying to find to do something in the university so that I can still get in touch with both subjects. And I find material science, which is an interdisciplinary subject that lies in between both of them. And what's more, material science also combines, it also involves many other disciplines like engineering and even biomedical science, which is quite exciting to me because I love to learn new things, like things that I previously don't know, and I love to find connections between different subjects. So I think material science is a great thing for me to do in a university.
Okay, so it's the combination of the different subjects and that makes it exciting for you.
Mm-hmm.
I've read your personal statement on your UCAS form, and you also say that you're fascinated in how the microscopic properties of materials influence how they behave on the macroscopic scale. So could you give me an example of something that you know about where that is true?
Okay, so one example of such is the probably some high temperature superconductors, where when you combine different elements like yttrium, oxygen, or copper, different things, when they come together in special arrangements, they become superconducting, and this such superconducting is highly dependent on their structures and the should I say the ratio, or the stoichiometric ratio, and but such and when you have these elements on their own, or if they're combined in other ways, arranged in other ways, such superconducting would not exist. So this is, I think, is one of the examples where microscopic structures will affect the macroscopic performances and properties.
Okay, that's a very good example. It's quite a complicated example as well. But if you had to condense it a little bit, which properties is it that's important in that case? Is it the properties of the electrons that are important? What is it about how the atoms are arranged that influences in this case, their electronic properties?
I didn't dive much into that case, so I guess maybe it is the atomic orbits that so when they are placed in special arranged in special ways, the overlap and the superpositions of different atomic orbits will make there will be it will produce such an effect that superconducting become possible. I guess it's the case.
Yeah, but let's take a simpler example that you're probably more familiar with then. What about a metal? So what about a metal? What can you tell me about the properties of a metal, like copper?
Okay, so copper has high thermal and electrical conductivity, and it is due to the delocalized electrons within copper atoms, which is in turn due to I guess it's the overlap of the valence. The valence electron shell between copper atoms that allow these copper atoms to all of the in fact, all of the copper atoms in the copper lattice to share their valence electron and form a sea of delocalized electrons. So these delocalized electrons can conduct electricity, and also they can, since they can freely move around the lattice, they also conduct heat at a very fast rate.
Okay, so it's the delocalized electrons in metals like copper that contribute to its electrical conductivity and its thermal conductivity. That's good. So why then does something like glass, that's silicon oxide essentially, why doesn't that conduct electricity?
So in silicon dioxide, all electrons are just trapped or confined within the covalent bonds between silicon and oxygen. So they are not free to move around. They are not delocalized as in copper lattice. So they cannot conduct electricity. Good.
So it's cut. So those properties have come down to the local bonding, haven't they? The different kinds of bonding in the different materials. Good. So thank you for that. I think we'll move on to the first of the questions, the technical questions that we've got for you. So I'll go over to Jonathan at this point.
Okay, hi. Right. Okay, so we get to the technical questions, just to say that we might sometimes switch between questions quite rapidly. That's no reflection on you and how you're doing. It's just because we've got a lot that we want to be able to get through today. Okay. So right, let's see if this technology works. So I'm going to screen show here. So just bear with me 1 second. Okay. If that has worked, can you now see a graph?
Yep.
Okay. So what this, and you might want to just take your pen and paper and make a quick sketch of what this graph is, and I'll tell you what the axes mean. Okay.
Okay.
So this is a graph where on the vertical axis we're representing the energy of a crystal, an arrangement of atoms. And on the horizontal axis, R represents the separation between those atoms. Okay, so this is how the energy varies with separation. Now, I'll tell you one other piece of information, which is the force on those atoms is given by the derivative. It's given by dE by dr. Okay. So what I'd like you to do is to describe for me in words how the force on the atoms changes as I move them from a very small separation to a larger separation, according to the graph.
Let's see. Okay, so I first have to draw the graph of the derivative. Hold on.
Well, I wonder if you could actually just, rather than draw it, because that might take a little bit of time, I wonder if you could sort of describe it in words for me.
Okay, so I guess since I'm seeing a minimum energy on the graph, I guess there should be an equilibrium position for I mean, the equilibrium separation between two atoms, which is right at the minimum point there.
Okay.
And beyond that separation, the force should be attractive. That means the force is trying to bring the two atoms together back to that equilibrium separation. But if the two atoms come closer than that separation, the force would become repulsive to try to get the two atoms apart and again back to that equilibrium separation.
Yeah, I absolutely agree with all of that. What I'd like you to just tell me now is, so I stopped the graph at a certain point. Okay, so I drew it for a certain value of R, and then the graph stops. But in reality, we could continue this graph. How would the graph look if I was to extend that red line to larger values of R?
I guess the energy should I guess it should tend slowly towards some limit.
Okay, I don't disagree with you, but could you talk about it in terms of the gradient, in terms of the force?
Okay, so so the gradient would still be positive, but it will gradually tend to zero. So the force will still be attractive, and it tries to it still tries to bring the two atoms together, but as the two atoms become further apart, that force should gradually diminishes.
Okay, great, thank you. Okay, I'm going to just change and show you a different graph. Can you see the red and the blue curves now?
Yep.
Okay, so what I've got is I've got two different what we might call allotopes, so two different arrangements of the same type of atom. So, you know, something like diamond and graphite. And I'd like you to tell me something. If I was to give you a cube of the blue material and a cube of the red material,
Mm-hmm.
what would some of the differences between those materials be? So just take a moment to think about some of the differences there might be between a sample of a material corresponding to the red curve and a material corresponding to the blue curve.
Okay, so I noticed that the two materials have different equilibrium separations. So, for example, in the materials that corresponds to the blue curve, the atoms should be spaced closer to each other, to one another. So I guess since both materials are made of the same atom, but in the blue material there's smaller separation, I guess the blue material should be denser. I mean, greater density.
Yeah, I agree. Yeah. Okay. Anything else you could so we could certainly see that we could compare the weight of these two samples. What else would be different? Could you tell?
I also noticed that the blue curve has greater gradient on both sides of the equilibrium separation. So should I find greater mechanical strength in the blue material, since the greater gradient suggests stronger force between atoms?
Okay. Yeah. I don't disagree with you there. Can I just, what would happen if we did it? Let's think about if you took these samples and you tried to compress them.
Mm-hmm.
Which would you find easier to compress, the red one or the blue one?
I guess the red one.
Yeah. Okay.
Is that really strength, do you think, that you're measuring there, or is it some other property of the material?
I guess, should I say the elastic modulus, like the Young's modulus?
Yeah, so it's a measure of the stiffness, really, isn't it? How easy it is to compress something. Good.
Okay.
Okay, great. I think I'll leave that question there and I'll hand back over then. Stop sharing.
Okay. So I've got another different question for you. This is a question about estimation. So what I'd like you to do is to estimate what area of graphene you think you could get from the lead of a normal pencil. So the lead is just the bit along the inside, the bit that you write with of a normal pencil. Can you estimate what area of graphene you might be able to get from that?
All right, so okay, so I think I should start from the total volume of graphites that I can find in a piece of pencil. Okay, let's see. How long is it? I guess 1.5 palm, 1.5 of my palm. So it should be I guess that is 15 centimeters.
That's fine. Yeah, we only have to be sort of the order of magnitude. So I'm happy with 15 centimeters. Yeah.
All right. Okay. So the diameter, I guess. So the diameter of the graphite in the middle should be around 4 millimeters. So the radius is 2 millimeters. And
that's fine. It's the right order of magnitude. It's probably a bit bigger than the actual lead, so you can make it 1 millimeter if you like, the radius.
right. Okay, so 1 millimeter. Okay, so that's 10 to the power of -3 meters. So for the total volume of graphite I'll get should be -3, -6 times 10 to the -2, 1.5 pi. So I'll give it 5. So the total volume of graphite in a piece of pencil should be 5 times 10 to the power of -8 meters cubed.
Right, let's just make sure the orders of magnitude are right. So the 10 to the -6 comes from
comes from the square of the radius of the graphite core, which is in the order of 10 to the -3.
Yeah.
And the 10 to the -2 comes from the length.
But is that right if you've got 15 centimeters?
I guess so, 15 centimeters. So that's a piece of unused pencil.
But is 15 centimeters 10 to the -2 meters?
Oh, sorry. It should be 10 to the power of -1. Yeah. So yeah. So that should be 10 to the power of -7 meters cubed.
Okay, good. I think I agree with that.
All right. So then I need to find the thickness of a layer of graphene. Is it?
Mm-hmm.
So I guess I can just take the thickness of a layer of graphene to be just the diameter of a carbon atom. Is it?
That would be a good starting point. Yes. Yeah.
So for that one, I guess the thickness of graphene should be about 1 angstrom, which is 10 to the power of -10 meters.
Okay. Yeah. So you've got the order of magnitude absolutely right. I'm just going to ask you to think. Graphene's essentially one-dimensional sheet, but what's it like inside the graphite, which is what is inside the pencil? So can you describe what the structure looks like inside the graphite?
Okay, so in graphite, graphite is essentially made of multiple graphene sheets, and these different sheets are bound together by weak van der Waals force, I guess.
Okay, so which separation, which distance is important in terms of working out the sort of thickness of a layer of graphene is what you're talking about?
I guess it's just because like all these carbon atoms are arranged in the same plane, so I guess the thickness of this plane is just equal to the thickness or just the diameter of the carbon atoms in the plane.
So that's going to tell you about the separation of the carbon atoms within the planes, but when you make graphene, you're separating the planes. So what about the distance between the planes? Is that the distance that you really want?
Oh, so there are okay. So I realized there are a lot of spaces between these graphene sheets within a piece of graphite, but I'm not sure about the ratio between the separation and the thickness of that sheet of graphene.
Okay, well, let's just do an order of magnitude. So the size of the carbon atom, you said quite rightly, is about one angstrom, there or thereabouts. Mm-hmm. So what about the separation? Do you think the length of that van der Waals bond between the sheets? Is it bigger or smaller than an angstrom?
It's definitely bigger than an angstrom, but I'm not sure whether it's 10 times or 100 times bigger.
What would your guess be?
I'll guess 100.
I think if it was 100 times bigger, the whole thing the forces would be too small. The van der Waals force would be far too small. 10 times is better. It's probably nearer 5 times actually. It's around 5 angstrom, that separation. So you can use 5 angstrom.
Okay, so So the separation between two graphene sheets is about 5 angstrom, is it?
Yeah.
So I now have 5 times 10 to the power of -7 meters cubed divided by 5 times 10 to the power of -10 meters. That is 10 to the power of 3. So that's 1,000 square meters of
Excellent.
graphene.
Yeah, it's quite remarkable, isn't it, how much graphene there is inside a pencil?
Yeah.
Great. Well, thank you very much. That's the end of that question.
Okay.
Jonathan, have you got anything else you'd like to ask?
Yes, I think we've got a few more minutes. So I'd like to ask us a materials question. So Oxford is the best way to get around Oxford as a city is to cycle. Okay. But I need to buy a new bike. Okay, a new bicycle, and I've been to the shop, and they will sell me a bicycle with a steel frame, a bicycle with an aluminium frame, or a bicycle with a carbon fiber frame. And I was wondering what your view was as a material scientist on which of those frames I should pick. What would be some of the good points or the weak points of those materials?
Let's see. So I guess in this case, so my first thought is that if you take out the price factor, then carbon fiber should be the strongest material among the three, which is steel, aluminium. Is it aluminium or aluminium alloy?
Oh, that's a good question. What is an aluminium? What is an aluminium alloy?
I guess aluminium alloy would typically consist of aluminium and, I guess, would it be silicon or?
It would be another atom, but probably silicon's, I think, unlikely. It's normally another metal. Why would I make a bike out of an aluminium alloy and not pure aluminium?
I guess out of a greater specific strength, so probably a piece of aluminium alloy will be stronger or stiffer than a piece of aluminium of the same mass or the same size.
Yeah. Okay. Let's just compare, say, the steel bike and the aluminium bike. What would be the advantages and disadvantages of those two materials for making a bike frame?
Okay, so steel is definitely stronger than aluminium. If you're talking about the same mass, but steel is way heavier. It has greater density. So but on the other hand, I guess the unit cost of making a piece of aluminium should be greater than that for making a piece of steel. I mean, if you're talking about the same mass, because aluminium is more difficult to extract aluminium from aluminium ore than to extract iron from iron ore, I guess.
Do you think if you have an aluminium object, say an aluminium can, or maybe even a bike, do you think all of that aluminium has come directly from the ground? I mean, where's the aluminium come from?
Oh, so some part would come from the ore, but majority, should I say majority? But at least some of the aluminium will come from recycled aluminium materials.
Yeah. So we get a lot of aluminium can be recycled. Yeah. Okay.
Right.
What about and that's one of the things in Oxford is it and England in general is it does tend to rain. So is there anything else I should be worried about in terms of a material to make a bike from?
So I guess corrosion is not an issue for aluminium because it's always coated by a thin but dense layer of aluminium oxide, which is actually transparent but so invisible, but it's still there. So I guess this dense layer of aluminium oxide would prevent aluminium from further oxidation or corrosion from the rain or other chemicals in the rain. But if you're looking for a steel frame, I guess you will need to make a stainless steel, which is essentially just adding some chromium, I guess.
I mean, actually making a whole bike frame out of stainless steel would be really quite expensive.
Yeah, indeed.
So let's say we can't make a stainless steel bike frame. What else could we do to make sure the steel didn't rust away very quickly?
I think we need to paint the frame with some with some paint to prevent the contact with the air, or which is with the rain, the moist air.
Yeah, most bike frames are painted for that reason. Okay, Susie, anywhere where you want to take this?
No, I think that probably we've explored enough today. So thank you ever so much for your time, and it's been very helpful for us to find out extra information about you. So thank you again for agreeing to be interviewed today. Okay, so if we think back to the beginning of the interview, we started off with a discussion of materials in general and why he wanted to do that. And he seemed to be quite clear. He seemed to know what the subject was about. He was quite clear that it involved the different elements of the different science subjects he was studying, and also liked the sort of engineering aspect that came in. So was there anything that you felt about the motivation that worried you or you thought was particularly good?
No, I think that was quite straightforward. He sort of clearly articulated that, and we didn't need to really spend very long on that at all. Yeah.
And then we asked about something loosely based on what he'd mentioned in the UCAS form, which is something I try to do personally, but not all college tutors do. And in this particular instance, I asked him for a specific example of something that he had mentioned in his form, and he gave a very complicated example, high-temperature superconductors, which I wouldn't have expected a student at the A-level stage to know very much about at all, and not as much as he knew. Of course, he's done the first year course, so he knows a little bit more. But what we did was quickly took it back to a simple metal and conductivity in a simple metal and how that relates to bonding, which is something that is more familiar based on the A-level syllabus. And I think he did a pretty good job of explaining why metals are conducting based on what's happening to the electrons. And we pushed a little bit further into why some other materials don't conduct electricity in the same way. Was there anything there that you wanted to pick up on, Jonathan?
Yeah, I mean, I think he had the rough idea of what was going on. I wasn't expecting something that was super precise from him, but it was kind of clear that he's interested in the subject. He's probably thought a bit about it. He's heard things in class, but has probably gone and read around a little bit, and was able to give a good explanation of sort of metals versus insulators that was appropriate for the level, I thought.
And this is something we often do, is to take it back to something familiar that they've learned about, like types of bonding and how that influences properties, which is something that's covered a lot in the sort of school syllabus. So it's good to see how they can use that information that they should be relatively familiar with in this context. Okay, so then we went on to your question, Jonathan, on the graph.
Yes, and in a way, this this question looking at the energy between two atoms. that people have seen, sometimes they've seen these graphs before, sometimes they haven't seen these graphs before, and the question takes a slightly different route. But people are able to hopefully think through logically what's kind of happening to the forces between atoms about a compression and expansion and things. He was obviously quite familiar with this graph, and we went through that very quickly. There wasn't worth spending too much time. I like the fact he found where the equilibrium point was, so I didn't need to push him on that.
I think it's probably unusual that he jumped straight to the equilibrium separation at the minimum point. I think that terminology and use of terminology is probably something he's picked up during the first year of the material science course, and probably isn't how an A-level student would maybe express themselves. But all the same, he could then explain what he meant by that.
Yeah. So sometimes what we might have talked about is where is the gradient zero? So it's a force. Or if the force is zero, that corresponds to the energy being a minimum. So sometimes there's a bit more of a discussion around what these things actually mean, and that's absolutely fine when people don't have that knowledge to hand, but they're able to take some hints and work it through.
Yeah.
But that first graph is really setting up the more interesting question, which is then to look at the two graphs, the red curve and the blue curve, and to talk about the materials. And again, he kind of, as a first year material student, I think he knew what type of properties to go and think about. And I would normally expect, I think, to give a sort of a hint here about saying, well, what about the equilibrium separation? What does that mean for holding two properties of the sample, and that gets you to density? And then, maybe asking, well, what happens if I squeeze the materials? How do those things compare? So I'd normally expect to give a few hints on this, and that's absolutely fine. But he gave good answers, but we made him be a bit more precise about what we meant about the strength of a material.
Yeah, and again, that's something that we may not have pushed on with a student who had less knowledge base to start with. So what we try to do is to find where their knowledge is, and to just push a little bit further if we can, to see if they can explain something. But we don't expect everybody to know the difference between strength and stiffness at this point. Some people may, but not everybody will, and that's not what we're judging really in this question. Okay, so that's good. So that was the graphs question, and this sharing of screens that Jonathan did there is something that we do in some of the interviews, not all of them, but some of them. And then we went on to the graphene question, and again the question was asked in a rather simple way. Of course, not everybody may be familiar with what the structure of graphite's like, or the structure of graphene, although I expect that's something that most people have come across at school. But we're quite happy to help explain that and to break it down if students need that. It was really a question on estimating. So none of the stages were very difficult, but there were lots of orders of magnitude that needed to be kept in mind. And obviously, it's very easy to make a slip, as the student did with orders of magnitude. It's very, very easy to do that. But the idea of being comfortable with making some estimates on sizes, the difficult one there is really estimating the separation between the sheets of graphene in graphite. And again, we don't really mind too much about the numbers. The question is whether they've been arrived at by a sensible thought process. So it's a multi-stage problem, but none of the stages in the problem are very difficult to do. And the actual numbers we're not too worried about. So making sort of estimates of orders of magnitude is absolutely fine for this. And again, depending on how quickly the student or the candidate is doing the question, we might ask more detailed questions about the choices they're making, like the separation of the layers. And it just depends on how things are progressing, quite how much we probe there.
Yeah. I have a feeling he didn't actually write the numbers down on a piece of paper, and I think normally that would have been, particularly in a real interview, would be probably good to write them down, because it's very easy to forget and get a little bit confused. So probably should have written them down on a piece of paper clearly, for him, just to keep track for himself. Yeah.
And there are other ways of working through that problem, actually. You could do it from various different viewpoints. So he chose one that was quite successful, and as interviewers, we don't try to push people into a particular way of solving a problem. We're interested in how they go about solving it, and there are several ways you could think about it in this case to get to the same sort of answer. Okay, so finally, the material selection bike question, Jonathan.
Yes, so this is a question that really can go in lots of different directions. So it's very open, and it's kind of up to the students in a way to sort of pick a way into it. I think he wasn't probably a really keen cyclist. I've had racing cyclists in the past that have given me very sort of specific answers about things, but that's fine. The question then will go in a slightly different direction, and it's really just trying to have a bit of a conversation and see if people can justify some of the statements they're making. So there, he raised a question about, oh, is this aluminium or is this aluminium alloy? And, well, okay, you tell me which is the more sensible to make the bike from. Of course, he's done a course in the first year on alloys, so that would be sort of primed in his mind. But yeah, and so with that one, we got onto corrosion, which is just one of the different directions we could have gone, and we didn't really say very much about the carbon fibre, but we were pushed on time. Yeah.
So again, we're not looking for a right or wrong answer there. There's lots of different things you could say, and it's a question of we're happy discussing anything that's sort of relevant and interesting, rather than us trying to push you down a particular route. But of course, if people are completely flummoxed by where to start, then we'll give a bit more guidance on getting you going with something. So it just depends on individuals that we, during the interview.